whenever there's a physical implementation of an information, so charge, you can measure that charge. If you can measure the charge, no matter how well you hide that, you can copy it. Okay, so that is one of these paradigms that you start this quantum information business from. Now, you start to make your physical objects smaller and smaller and smaller, and eventually you end up in the smallest thing you can measure. Okay, and that is a domain where quantum mechanics comes in. So if you use a quantum particle as your Fourier, okay, say a single photon, then you have to ask, how often can I measure a single photon? Okay, and it turns out that if you try to copy information or measure a single photon or a single quantum particle, then slightly different laws of physics apply. In particular, if you measure a few times a particular property, then you leave traces. And you leave traces in a way that are not determined by a promise of a manufacturer who says whoever tries to read that device leaves, I don't know, a blob or the self-destructs itself. It leaves traces because of the fundamental laws of physics. Okay, and that is one of the promises this quantum key distribution can do. How does that work? You start. Well, the question is how do you encode information in a quantum particle in the first place? And one simple way of doing that would be using a polarization of a photon. Now this laser pointer here spits out many photons, so that's why you can see it. If you just have a source which just spits out one by one, you can still use that photon to encode information. For example, you can just encode it in the plane of polarization. So if this laser, I don't know, oscillates, the electrical field of this laser oscillates, say, in one direction, and depending on how I turn this laser, I don't know whether I can see that. Oh, you can see, well, you cannot see polarization, but sometimes it has an odd shape.
I think we have a polarizer, we can try it.
Oh, we have a polarizer, okay, we have a polarizer. This is gadget time. I'm not sure whether this works for the green light.
This is the polarizer for infrared.
so
this upgrade to the green laser maybe wasn't such a great idea.
It's a bit improvised here. Well, while Anthia's packing up the toys here, let's just try to show how do you measure a polarization or the information, how do you get back this information of a 0 and 1? And we typically don't use these sheet polarizers, we use a polarizing beam splitter. Polarizing beam splitters are can be based on birefringent material. You maybe have seen all these physics books, these calcite prisms and all this nonsense. Basically these devices allow you to, need this laser? You have another one? Okay.
I think it doesn't work.
It doesn't work. So you take your photon, one polarization goes through, okay, the other always gets reflected. That's what a polarizing beam splitter does. And then you have photodetectors which can see single photons. You make a single photoelectron out of it and then a whole chain starts. We actually have a photodetector here. It looks like a very boring device. If you just want to look at it, it just makes a photoelectron and you see a large signal out of it. So then you end up with a 0 and 1 out of your detectors. One trick is you can only detect a photon once. Okay, once you make a photoelectron out of it, it's gone, and all its polarization properties are gone as well. And this is somehow how this quantum key distribution comes together. But before we go there, you need to keep in mind that you can not only use vertical and horizontal polarization, so the plane of the electric field for that photon, but you can also use other polarizations. For example, vertical and horizontal polarization of 45 degrees and minus 45 degrees. Okay? As long as these polarizations are orthogonal or just perpendicular, you can encode zeros and ones into that thing. Now, quantum mechanically, that can be written as a superposition. Okay? So the 45-degree polarization can be written as horizontal plus vertical, and the other one as horizontal minus vertical. Okay? That is not too illuminating at this point. Why did we need this superposition principle here?
Because we thought that nobody would understand the following slide otherwise. So the idea is that before we had I didn't really mean it to sound like that, but the idea is that you have a beam splitter there, polarizing beam splitter, okay? And in quantum mechanics, if you have a polarization, there's no such thing as a measurement that says, what is that polarization? You just cannot ask that question. The only thing you can ask is it like this or like this? Or is it like this or like this? So you always have these binary options if it's for this particular dimension of Hilbert space. That was very clear, right? Okay, so imagine you have something like that, And you know, if you send light, just a laser beam through a polarizing beam splitter that would transmit horizontal and reflect vertical like there, and you reduce, so if the light is bright, you can imagine that if your light is polarized like this, half of it will be transmitted and the other half would be reflected. We're kind of used to that from high school. But now reduce the light level. You reduce it, reduce it, reduce it, and you end up with a single photon. And the single photon arrives to that polarizing beam splitter. What is going to happen? Will it be transmitted or will it be reflected? It's a single photon, so it cannot be split. It's a single quantum object. Okay, so it has to make a choice. And it's a completely random choice, fundamentally random choice. And the underlying reason is that it's a superposition of two different quantum states, a horizontal and a vertical one. Was that the reason?
Well, I forgot that line of thought, but one thing you need to keep in mind is if you try to measure a few times the polarization with such a polarizing beam split, okay? If you just choose, say, our vertical or whatever the red color was, and send it a few times through it, you always get the same result, okay? So it just always goes through all these beam splitters. Whereas if you use this 45-degree one, you get a completely random result, okay? So the outcome of where a 45-degree photon goes after such a measurement device is completely random, okay? But once you have your photon going along there, you can just send it through a whole chain of these guys, okay? So that was somehow there to show that you need to choose the correct measurement basis in order to get always the same result. And that is something which can allow you to have an eavesdropper revealing himself or herself in a communication process.
And it's also quite nice to get random numbers out of your system, because when you send this 45 degrees polarization, there's a 50-50 chance always. And this is really a random process.
Right, and some people sell you actual devices which make random numbers like that, or at least they say they do that. Right? So, yeah, now back to how do we encode information? So we know we always need to use two orthogonal polarizations of a single photon to send information from one side to the other side. And if you measure it in the correct basis, you get the correct result. So this is supposed to be shown here. You send one of the red and the blue ones, and you measure it in the correct direction, and you get a red and a blue result. Okay, or you send a green and black one, and you measure it in the whatever rotated basis, and then you also get the green and the black result. And you just make a connection: red is 0, blue is 1, green is 0, black is 1, and that way you can send over information. If you happen to measure in the wrong basis, you get a completely random result. Okay, and that is in a funky way. This is reflecting this Heisenberg uncertainty principle. Okay? This is where the physics really come in. You cannot measure horizontal vertical polarization and 45-degree polarization equally at the same time. This is fundamental physics. Okay, and there's really no way around that. Okay. Even if you're clever, there's just okay. Why does that not work? Ah, okay. Now you can use this table of measurement results and prepare results to actually send a secret key over to the other side, and that is referred to this BB84 protocol. So how does that?
So BB84 is actually two guys who published a paper in 1984. I think Bennett and Brassard. And yeah. And it goes actually back to an idea which is even older. So 1970, a chap called Steve Wiesner came up with this idea of making money which you cannot forge. He wasn't successful in making that, I have to say, but it still kind of ended up in this key distribution protocol. Now, how does that work? You have a light source which spits out single photons in the first place. Then you choose a random number. So I don't know, you need that one, which finally will make your secret key. You choose a way how you encode it, horizontal, vertical, or plus or minus 45 degrees, and send it to the other side. On the other side, you randomly choose what you measure. Okay. So another random number is needed here, and you get a particular result. Now, if somebody wants to listen in here and doesn't know what was the basis, what was sent, there's no way you can measure that without leaving a trace or an error with a certain probability.
And that is how you make sure that nobody has listened in into this communication process. So after the measurement result is done here, so your photo detectors, well, we always say they went click, but they actually don't make click. So I don't know. But anyway, you just get one measurement result that a photon ended up here or there, and then you say to the other side, hey, I was using one particular basis for detecting that photon, and if it was the same basis as the chap which has chosen to send a message to the other side, then they just keep that bit, otherwise they throw it away. Okay. So in 50% of the cases, you just end up with the same random number, but it's not really random, it's the number Alice has chosen here to send over to the other place to begin with. Okay, so, and then you try to find out how many errors did you actually find, okay? So, was there, well, you take all the random bits which were put in the first place on one side, and all the measurement results on the other side, and then you try to find errors, okay? And you find errors by just talking about parities on blocks and things like that. And if you discover that some of the parities are not matching, then you know that somebody has listened in, okay? And somebody was trying to steal your key. And there are actually reliable ways of doing that without telling somebody who listens to that discussion what the key really is.
So maybe two small remarks here. Although it's always phrased as quantum cryptography, it's always only a method to transfer a random number from one place to the other. So there's no message on the left-hand side coming into this game. So the message itself is afterwards transferred with encrypted with this one-time pad over the public channel. Yes. And also, this quantum channel is nothing funky. It's could be air, just photons going through air.
Yeah. Here's an example. I just needed to have the steampunk thing because this was one of the earliest implementations, 92 or so, by Bennett and Barsa. I don't know, John Smolin probably built that whole thing. So this was the first quantum cryptography kit. We have a light source, just an LED, okay? A pinhole, I don't know what that was for, a lens. This is a polarizer to make sure that you have a well-defined polarization of the photon, and then you modulate that polarization, and you choose a 0 and a 1, and you choose the horizontal, vertical, or 45-degree basis. You do the same thing on the other side, and you have two photodetectors, and one of these polarizing beam splitters, it was a Kelsa or Wollaston prism, to implement that. Now that looks very early-ish. Nowadays, these systems look much more compact, and but before I go to that, you need to really look into the physics. What is that really implementing this basic idea? Okay, and the trick is almost, okay, because for that whole thing to work, you need to make sure that you only have one photon, and that the information is not encoded in a strong light pulse. It's relatively easy to steal. I mean, if you have a big light pulse, a big light flash sending from one side to the other side, which is vertically polarized, then it's an easy way to listen into that by stealing a few photons of that bright flash, okay, and measuring the polarization there in any basis. So whenever the information is encoded in more than one photon, then you can steal that information. And what people actually use is not a single photon, but so-called faint coherent pulses. That is basically what comes out of that laser if I switch it on for a very short time. Okay, you switch that thing on for a very short time, and you do it just short enough, or you attenuate that light, and you get about 0.1 photons per pulse. Okay, that is perfectly possible, but there's a certain probability that you have more than one photon, and in those cases you can actually steal that information. So, despite the fact that it's relatively simple to switch on and off such a laser and create a small number of photons, you always have a possibility of listening in. And that is something you need to take into account if you build such a system. In our community, people refer to that as photon number splitting attack. That's one of the jargons. Does that work? Okay. There's also, if you look how people implement such a system, I just show a small thing, is that they typically don't use modulators, okay, because they're relatively expensive and complex. You just can use 4 different light sources with different polarizations and mix them together. Okay, so many systems just rely on such a geometry. And then you make sure that you cannot distinguish which light source was emitting your faint coherent pulse, And the system looks, I don't know, I had that around at some point a few centimeters in size, so it's reasonably compact. The polarization measurement,